Okay, so good afternoon, everybody, and welcome to this afternoon's lecture. My name is Sara Bonella. I am the Deputy Director of CECAM, and I am, according to the program, the Mistress of Ceremony for today's event, which I guess means that my main job is to keep things moving on time, and which also probably means that I'm already doing a very bad job at it, but we'll see how it goes. Apologies, we had a technical rehearsal yesterday, everything worked, and then now, of course, today, things didn't go as smoothly as planned. Let's see if we can convince you that it was worthwhile waiting for a little longer. So what we're trying to do today, and when I say we, it's CECAM and MARVEL, and we will also explain a bit more about both of these institutions for those of you who don't know them, is something slightly unusual for us. We have tried to organize an afternoon in which we explore a boundary zone in between history of science, and the people who actually did things that nowadays we take for granted. And when I say things that nowadays we take for granted, I am thinking about using computers and computer simulations to do science, both in terms of the science and in terms of using the computers. The structure of the afternoon at its core is a combination of two lectures. The first one will be delivered by Professor Michel Maréchal, who has a long and illustrious career as a statistical mechanician who's used computers and developed numerical methods to study systems in and out of equilibrium. He's now emeritus at Université Libre de Bruxelles. He also has a long-standing connection with CECAM, having been one of its directors. And he will set up the stage from history of science, or at least survey on some of the fundamental scientific papers and methods that started simulations as a tool to do theoretical physics and chemistry. This will be followed by a conversation between Professor Daan Frenkel, also an outstanding representative of people who do statistical mechanics using computers, equilibrium methods, molecular dynamics, Monte Carlo mostly, you name it, he's done something like that, who will be chatting with one of the pioneers of using computers in the sense of actually writing the codes that were used to do these calculations. And this is Marianne Manseid-Carlsen, who is our much appreciated guest for the week here in Lausanne. So let's see how it goes. We'll try to keep things running as smoothly as possible. I would like to start by asking Ignacio Pagona Barraga, who is the director of CECAM, to say a few words to open the proceedings. Thank you.
Hello, welcome everybody. After this explanation of what we're going to do, let me start by saying that indeed this is an event that we, CECAM, have decided to organize this year with MARVEL. It's slightly different from other events we have been organizing in past years, and it will be a trip to the past to see how fast we have evolved in the early 50s when simulations started to make his way in science. CECAM is an European organization. It's a bit younger. It's almost 50 years, though. Actually, it will be 50 in a couple of years, the same as EPFL. And it started due to the vision of an American scientist in Paris who understood that computer simulations were bringing a new way of understanding and working in science. And he also understood the relevance of international cooperation. So he set this organization that basically fosters international cooperation and organizes workshops and schools on a regular fashion. Started in Paris, moved to Lyon, and it's now here in the EPFL at the very end. So we are EPFL, but we are in the UNIL campus, so we're almost out of the EPFL, but there we are. And nowadays we have a network structure, so we have presence in quite a number of European countries. So that's also, again, a way to enforce this cooperation I was mentioning. Since 2 years ago, we started to organize the CECAM lectures as a way to bring to the EPFL community the sharing the science that is discovered in CECAM and what are outstanding, interesting problems. And we have had already 4 lectures in these past events. I will not name it, but you can see them in different aspects of computational science. And as I said, this year, this event is a bit different. And I hope you will enjoy really going back to the beginning, understanding how the pioneers developed the codes and established basically what has been successful molecular modeling that has developed so rapidly. And also, last but not least, we will, having Marianne here, we will also understand how women have strived in this world and how they have been able to contribute significantly since its very beginning. So I'll stop here, and we will start the real event now.
Thank you, Ignacio. Okay, so our first speaker for the core part of the afternoon is Michel Maréchal, as I said, and he will tell us about the early days of computational statistical mechanics. It's only numerics. Now, before he starts, let me just tell you what we have thought. We would like to keep continuity in between his presentation and the conversation between Dan and Marianne. So we would like you to wait before you ask questions until the end of the whole session. The speakers will, of course, all be here for the whole time. So, there you go. Take it away.
Thank you. Well, thank you to Ignacio and thank you to Sarah for organizing this and to whoever else has helped to organize. I think it's a wonderful idea. And I am delighted to be the speaker before and to introduce in a little way Marianne Manside. So I'm looking forward to hearing all what you have to say. Now, when you proposed to have an introduction talk, I was thinking that maybe the easiest thing would be to go back to basics. The really first few papers that have allowed this field to be recognized as a new and trustable way of making science. So I will do this. I have to be very careful because there is a button not to touch, I was told. Yes. So I will do this in the following order by first speaking about the background in the years 50s, about computing and scientists. I will then shift to introduce something very fundamental, which is known as Metropolis Monte Carlo. I will introduce also molecular dynamics, which is the other method to make molecular simulation. And I will speak about the history of how these two methods were able to convince the community by showing something very simple, which is that a fluid made of a model fluid of hard spheres, billiard balls, would have a first-order phase transition between a solid phase and a fluid phase. Now, this result was very controversial. There was absolutely no consensus in the community. And it was only by computer simulation that, not by experiment, but only by computer simulation that you could convince the community. And this was really a real effort that was convincing for the whole scientific community. Now, it's only numerics. What does this mean? Maybe you have already heard such a comment when comparing results in mathematical physics theorems or in some other field, and when you do the numerics, when you do the computation, some people say it's only numerics. Myself, I was with two known physicists and mathematicians, one physicist Joel Lebowitz and the mathematician was Sinai. And I was taking them downtown after a conference, and then they were discussing the talks of the day. And one particular talk was a Russian making a presentation, and Joel Lebowitz was very much excited. And he said, very good. And then Sinai said, but Joel, it's only numerics. And then, realizing that I was also there, me, director of CECAM at that time, he said, I'm sorry, but you know how we are. So, indeed, it's something that you may hear and hear all over again. It's only numerics. It's not something very serious. It just helps mathematicians when they are unable to solve an equation. But it's not true. It's a new way of doing science, and this is what I want to somehow try to explain. Now, in the year 50s, you had a few physicists and mathematicians that were convinced that computers were indeed useful. One of those is Enrico Fermi, that you may know from your classes in physics. And Enrico Fermi is supposed to be the father of the Monte Carlo method. He used to have a mechanical calculator in order to make a few computations. And after the war, when the first computers arrived, he was indeed doing a lot of computation. One of them is very famous, is the famous Fermi pasta Ulam model, but I will not speak about that. But in this slide, what is impressive to me is this is written by Enrico Fermi. So Enrico Fermi, the big physicist of the Fermi, Thomas Fermi model, or the Fermi distribution, was writing a program in assembly language in all details. So he was not simply one of these great mind that was able to do theoretical physics. He was also going to the numbers and to the real details of that. Now, that's not the case for everybody. Now, he's supposed to have invented the Monte Carlo method, which is basically using random numbers. When you want to have, for instance, a computation of pi, you may do it just by using random numbers or throwing stones in a circle which is inside a square. And by counting the number of times that you throw the stone inside the circle over the total number of throws, you will have pi. Now you can do it very simply with this algorithm, using not random numbers, but pseudo-random numbers. So the computer will generate pseudo-random numbers. And by collecting all these pseudo-random numbers in this way, so the number of times that the sum of two squares of random numbers are below 1, divided by the total number of throws, or numbers that you have generated, you will have an estimate. Very bad estimate, it does not converge. It's not to have a precise estimate of pi. There is something there that is... but it is basically the idea of a Monte Carlo method. Now, these two people are also well known. John von Neumann, you may have heard of the von Neumann equation. That was a brilliant mathematician during the last war. And Stanislav Ulam was also a brilliant mathematician, mostly known for having developed the hydrogen bombs, which maybe is not a very remarkable thing, but he was a remarkable mind. Now, in this letter, they arranged for a trip to Los Alamos. Los Alamos was one of those laboratories where you had computers, where you had, during the war, developed the bomb. So there were a lot of academic and scientists going to this laboratory. And in this letter, besides saying things about the family and so on, he was explaining to the colleague how to use an accept and rejectance method to have numbers not uniformly distributed between 0 and 1, but distributed along any kind of probability distribution that you want to impose between any values A and B. So that's a very simple thing to do. You first transform from 0 to 1 the interval into A and B. And then once you have selected a value, you would compare with another random numbers, these random numbers with the probability distribution at that value. And in this way, you would fill this area with a density that is proportional to the probability distribution. So that's called the acceptance-ejectance method. That's one of those methods that were developed with the computers by people that were not thinking that it's only numerics. With what kind of computers? Now, MANIAC was a kind of home-built computer in Los Alamos that was built by this personality Metropolis, Nick Metropolis, who has given his name to the Metropolis Monte Carlo algorithm. Now, what MANIAC means is mathematical and so on and so on. It's not very important, but it was one of the first computers available to the scientists. And in the process of the story that I'm going to tell you, we will shift from this MANIAC type of computer to commercial computers. The basic company were Univac and IBM, and I think you started working on these commercial computers rather than on MANIAC. What I'm going to tell you in more details, having set a bit background here, is this story that starts after the publication of one paper by Metropolis et al. In 1953, and that will last until a conference in 1957. And this short period of time, so 4 years, these two characters, Bill Wood in Los Alamos and Bernie Alder in Lawrence Livermore, that's in California, both have developed a method, the Monte Carlo method that was explained in this paper, and the molecular dynamics method by Bernie Alder, in order to show this result that I told you was a prediction by John Kirkwood, and that predicted this phase transition, first order phase transition for the model fluid of hard spheres. So I'm going to concentrate on that story, taking testimonies that from articles and interviews that were that are available in the literature. I have a list of references that will be online. Okay. So this is the starting point, the basic starting point. It's an article written by 5 people, starting with Nicholas Metropolis. So the algorithm that is described there will have the name of associated with the first author, Nick Metropolis. It's, some people say, the most important algorithm in computation, but it's among I would say, the 10 most important algorithms of computation. It consists of the following. If you have the occasion, take the article in the library and read it, because it's very simple. It's very easy to read, and it's beautiful. It consists in computing the equation of state of a system. In order to do that, you don't have to worry about the velocities of the particles. You have only to worry about their positions. At equilibrium, the velocities are something trivial you can integrate. Now, for the position, you may use, or the idea was to use a Monte Carlo method. That is to throw the particles at random. But just throwing the particles at random, like you would do to compute pi, is very inefficient. Because most of the time, the particles are in positions that are not likely to happen. And then, once you have a random configuration, you give them a weight that is given by statistical mechanics, that is the Boltzmann weight, exponential of minus the energy divided by the temperature. Now, doing that is very inefficient, And the idea was to change, in fact, the procedure. And this is very well explained in this article, that you would start from a configuration, and then instead of having a random position for these particles, you would make random moves. But random moves that would not disturb too much the system, that would make it look like an equilibrium or a low energy system. And then you would use this method, the accept and rejectance method, in order to generate, in sequence, configuration in such a way that they would have a weight given by the Boltzmann factor. And then it is explained here in more details. So make a random move of particles, and then accept or refuse the move with a criteria that would allow you to have this distribution, not any distribution, but the Boltzmann factor E minus beta H. And this is explained here in more details. And then once you have generated all these configurations, you just make an average over the configurations. You don't have to weight them anymore. So you replace this Boltzmann weight by an arithmetic mean of configurations which are generated along a procedure that would provide you with a sequence having the correct Boltzmann weight. So it's something very well described in the article. And as I told you, according to Google Scholar, 30,000 citations. It is the most important paper, I would say, in molecular simulation, and one of the most important papers in algorithmic developments. Now you see here also that there is a reference to Bernie Alder, who is doing something very similar at the same time, but we will come back to that later. Now this is a Metropolis Monte Carlo. This is an interview of Marshall Rosenbluth, so the second author, or the third author was first the wife. And this interview, here he says, well, the idea comes from Teller. So Teller was one of the authors. Teller is I guess maybe you know a few equations named after his name. Maybe you know that he has been involved in the development of the hydrogen bomb. And maybe you have seen the movie Dr. Strangelove, because he was the character inspiring the character in the movie of a crazy scientist. This was Teller. Teller had many ideas, and then he gave an idea. One of his students, there was a postdoc, was Marshall Rosenbluth. No, he was a student, so he got the PhD with, Marshall Rosenbluth got the PhD with Teller. And he gave the duty to Marshall Rosenbluth to do it. So Teller had the idea, and then I worked out this appropriate algorithm for doing that. And then the questions are, but what about the other authors? Well, there is a wife of Rosenbluth who did all the coding, which at the time was a new art for these machines. But there is also the wife of Teller. Well, Teller's wife during the war had been one of those computer women. He wanted her to get back into the work, but she never showed up. So she was basically put on the paper. Yeah. Yes, as was Metropolis, I should say. Metropolis was both a computer laboratory. We never had a single scientific discussion. That's why the algorithm is named Metropolis Monte Carlo. So one has to be extremely careful in giving credit to people. And this is very likely to be true. Now, in this article, there are three things which may be important for our story. The first one is You have an accept and rejectance method. You make a move, you accept it, fine. This is your new state. And from there, you make another move. If you reject it, you stay at the initial state. But should you count this initial state once again? Or you just try to make new moves in order to have a successful one? And Rosenbluth explains very well, yes, indeed, you have to count that state again. So if you try to make a move and you are not successful, well, the new state is the old state. And you count it once again. Now, there had been a lot of discussion in the community to know if this was correct or not. Everybody believes that it is the correct way. And it was already a forbidden move. We count again the initial configuration. Not to do this would correspond to removing from the ensemble those systems who try to move. So there was already an evidence for Rosenbluth that this was the correct procedure. Now, in the case of hard spheres, so hard spheres are just billiard balls that do not penetrate each other. They have an infinite repulsion energy when they touch, and otherwise they don't interact. In that case, you make a move, there is no overlap, no change in energy. If there is an overlap, the energy is infinite. So the move is accepted or rejected, but there is no in between. It's either there is overlap, you refuse, either there is no overlap, and indeed you accept. So that case is much more simple than when you have an energy that changes because of the position, and where you have to make the computation of the difference of energy. Now, in that case, there is in the paper I mentioned just before, a reference that Bernialder and others were also doing a similar computation, and indeed, they were doing similar computation with hard spheres. So they had developed independently the same algorithm, but for hard spheres. And they published a paper later, but they published this paper where you see something which is a radial distribution function. Now, one can see in this radial distribution function probably the existence of a solid state structure, because the maximum of this function is not at the initial position here. This is a distance between two particles. This is the probability that you find another particle at that distance, and you see that you have a maximum that is at a finite distance, the first neighbor in a solid-like environment. So they had already, Bernialder was doing the same, but independently, had probably already touched the solid state in that case. And finally, I say that the paper of Metropolis et al. Is very important. It's important for the method, but it is absolutely not to be trusted for the results, because they had a statistics which was very poor. And they didn't see any indication of a phase transition. But we will see in the end that there is a phase transition, and that they missed, in fact, the physical result with the most beautiful algorithm. Now, back to our two characters, Bill Wood and Bernialder. The prediction of the solid state was made by Kirkwood. Kirkwood had two students, Bill Wood and Bernialder. So he convinced them to work, and he arranged with Rosenbluth that Bill Wood in Los Alamos would work on the Lennard-Jones and hard spheres, and Bernialder, who was in Livermore, California and New Mexico, would do something else. So the first thing that Bill Wood did was to clarify a bit the signification of this algorithm. And it's funny, this is things that he had been writing. So you can see in his memories how he understood what was the algorithm doing. He said, one day I met Marshall Rosenbluth in a hallway. He mentioned that he had seen a book on probability theory on the shelf of the library, and that he should probably have a look because it's exactly what he is doing. And the book was a book of Feller on probability theory, which you may have used during your studies or which you will use in a... It's an important, extremely important book, but that made everything clear in a way. You go from one state I to a state J, you have a probability to go from that state to the other state. You are doing a random walk with a finite number of states, a discrete in space, discrete in time, a random walk, which is a realization of a random process called the Markov chain. A system is a Markov chain when you have this probability distribution that do not depend on the past. When you are in any state, you have a probability to go to the other state from I to J. And this probability do not depend on how you have come to the state I. So you forget your past. It's something very comfortable in most of the human situation. Forget the past. This is what the particles do in this scheme, in this random. It's not true in general, but in the modeling in the random modeling, this is true. The system has to be ergodic. You cannot separate the space of states into these joint sets. So you should be able to go from any state to any state. And then, using the theories for probabilities, you show that your algorithm is precisely a realization of a Markov chain that would converge to the ensemble average. So you are just doing one thing that has been stated by mathematicians and that show you rigorously that you converge to the Boltzmann average of the system. And the important thing here is that you need to respect a fundamental rule in that game. It's called detail balance. What it means is that the flow of probability from I to J should be equal to the flow of probability from J to I. Not that the probabilities are equal, but the flow of probabilities from one state to the other should equilibrate. For all pairs of states, you should equilibrate this flow of probabilities. And that's a basic, in statistical mechanics, this is really basics for equilibrium system, even sometimes non-equilibrium system. But that means also that you can choose other kind of transition, other way to proceed for the algorithm. You can bias Monte Carlo, or Metropolis Monte Carlo, or Rosenbluth Monte Carlo. You can bias it the way you want, provided you respect detail balance. And this is, of course, something extremely important because it will allow you to explore in the configuration space a lot of regions that you would not go very naturally to explore. So, with this clarification, they started to do the computation in Los Alamos. But before speaking about that, Bill Wood, student of Kirkwood, was interacting with Kirkwood, and in this interaction, he had to convince Kirkwood that he was doing the right thing, which indeed he succeeded in doing that. But in a letter, according to Bill Wood, the common Marshall's argument, so this is Kirkwood writing, Marshall's arguments were at no time helpful. A new mode of presentations were very opaque. But from that time, he was an active proponent. So you see, the character of Kirkwood was not so easy to in a way. maybe take it as an encouragement if you go to your advisor or if you go to a colleague that is a bit negative, take it as an encouragement to continue with your ideas. Now, so they started the computation on Lennard-Jones and hard spheres, but the results were not published until 57, and we are in 54, because we got distracted by the disagreement of the Alder and Wainwright molecular dynamics results. Okay, what's that? So Bernie Alder was at the same time developing another method. Instead of doing this change at random, do the exact dynamics. Well, for real, not real, for realistic potential, this was at the time too costly. Molecular dynamics really started for regular potential, not hard spheres, but really like Lennard-Jones potentials in the mid-60s. So in 64, 65, started molecular dynamics because the computers were able to proceed with the computation at that time. But before, it was only with hard spheres that this could be done. Now, how do we do that? How did Bernie Alder propose to do that? Well, these hard spheres are just moving trivially according to their velocities, and once in a while they collide. So you compute the collision time for all the pairs that you have in your system. You look at the shortest time, you update the system until that time, and then you make the collision that is with the shortest collision time. You perform the collision, which is just something like a reflection, like a specular reflection of the relative velocity. You make that collision, so you change velocities, trajectories are changed, and then you look for the shortest next collision time, and so on and so on. That's an exact computation. You are not making any approximation except for the round-off error of the computer. Otherwise, you compute the exact trajectory of a system of hard spheres. And that's what Bernie was doing. So these are photographs that were published in an article in Scientific American much later. So it's not in the story. It's just to illustrate what he was doing to compute the trajectories of particles in a state that looks like a solid, in a state that looks like a liquid. So you have these trajectories of particles, and I think that Marianne was responsible for the display of these trajectories and the publication in Scientific American. And then, in a region where you would have possibly the two states, you would see that the pressure in time would go from one low state to a higher state. So that you may suspect that because of this change in time of the pressure, you have instead, not instead, but you have as an explanation a change of the structure of the system at the same time. Okay, he was doing that, and I'm going to show how these studies, so Monte Carlo in Los Alamos and molecular dynamics that was in Livermore, Bill Wood and Bernie Alder, how this proceeded and how they converge to the last point, which was in fact the conference in Varena in 1957. But before that, there was a conference in Brussels where there was a first explanation of what was molecular dynamics, and then another conference in early 57. So these are the three steps before we come to the end. This is a Brussels conference. You probably don't recognize many of these people, so I will help a bit. And First, you have these 6 names, which, well, George Uhlenbeck had already got the Nobel Prize in physics, but the 5 others would get the Nobel Prize later. 3 physics and 3 chemistry Nobel Prize. Onsager, Prigogine, and Poppel for chemistry, Guppert, Meyer, De Gennes, and Uhlenbeck for physics. You had Kirkwood somewhere there. Bernie Alder is our hero now, is there. He's looking a bit tense because he had to confront this assembly. Probably he was the next speaker, and manifestly he looks a bit scared. Now you have a few other names. Nico van Kampen, Joel Lobowitz. Van Hove is the one speaking. Van Hove is a non-physicist also that ended his career as a director of CERN. And a few others that I have not been able to localize, but which are well-known names in statistical mechanics. Now, the 6 Nobel Prizes were not given for statistical mechanics. They were given for other subjects. But you have a lot of people there, what we call la crème de la crème. And you have to present them your results on molecular dynamics. So basically, what Bernie did was indeed to show what he was doing, and that somehow what he was doing was reasonable. So these people before were meeting in Brussels because they were excited about developing kinetic theory. That was the main topic at the time. Do what you may have heard of the Boltzmann equation, which is an extremely beautiful equation, but which is only valid for dilute system. It describes the non-equilibrium state of a dilute system, of a dilute gas, of the gas of this room, for instance. And they wanted to extend that to the liquids or to the solids, to the condensed phase. So they were thinking that this Boltzmann equation could be generalized by a kind of a density expansion like was done in equilibrium. So Bernie Alder coming and explaining what he was doing, he tried to do something which is, I'm able also to describe time-dependent phenomena, irreversibility, system going to equilibrium, and so on. He was computing the so-called H function, which is the entropy of the system. You go in a manifestly irreversible way from any non-equilibrium state to equilibrium with a monotonous decrease of the H function or monotonous increase of entropy. And he was also showing this time correlation function for the velocity of the particles. How a particle will lose memory of its velocity in time. He mentions also in the article that there is a discrepancy between the equation of state, but this is 2 lines, discrepancy between the results of the equation of state with the result of the Rosenbluth, so the Monte Carlo results. That's it. Now, before, when I was preparing this talk, I sent a mail to Joel Lebowitz, who was one of the participants, asking, how was this received? It's only numerics. I mean, he got the polite interest of the people, but showing that he was just doing something reasonable was of no interest to this crème de la crème type of set of physicists. Now, it's very ironic because, in fact, this time correlation function for the velocity, it's not an exponential. He says it looks like an exponential. So when you have hard spheres colliding and they are at equilibrium, and you look in time how hard spheres will lose memory of its velocity because of the interactions with the others, the usual belief was this would decay like an exponential. It would take 10 more years to Bernie Adler to publish a paper that was first rejected by the referees, as he says, but he convinced the publisher finally to publish on what is called the long time tails. That in fact you have a long time memory for this function. And that is explained by a kind of collective effect and hydrodynamic vortex that you create whenever you transfer momentum to the fluid. And that article, which is a very profound article, it's just three pages in Physical Review Letters, in fact is linked to the profound cause of the failure of extending the Boltzmann equation to higher densities. So the problem that in fact was so fascinating for this conference, the answer was in this method that got no interest at the time, and it would take 10 more years to Bernie Adler to get a computer that would give sufficient confidence in the statistics obtained. So it's a very ironic situation, but somehow we can say that retrospectively with a judgment now, but at the time it was very reasonable to say, well, this is just only numerics. Now let's go back to our story. And then there is some disagreement with the Rosenbluth results. Now, the thing goes that they meet. The guy doing Monte Carlo in Los Alamos and the guy doing molecular dynamics in Livermore, they meet. And they decide to redo all the calculations and to compare their result by one method, which is a Monte Carlo equilibrium system, and the molecular dynamics with the time dependent of the trajectories, and they would compare the two methods. Now they start doing that. And with Monte Carlo, they very quickly find, for Lennard-Jones, more or less a phase diagram, and for the hard sphere system, they show some evidence of a first order phase transition. But the molecular dynamics didn't see it so rapidly. So there was still some discrepancy between the two. So much that the second conference, that was in January 1957 in New Jersey, there was a symposium and where these results were discussed. I was not present, says Bill Wood, but Kirkwood presented our results, including the phase transition interpretation. Adler argued against it at the time. Now, it's a bit funny because in these discussions, the audience was a bit divided. So they had a vote, I think, and then at some point they voted 8 yes and 8 no. 8 believing that there was a first order phase transition, and 8 would say, no, we don't think that there is enough evidence, or we don't believe in the result. But the result was not so convincing at the time, with one of the proponents, Bernie Adler, arguing in a strange way against it because his statistics were not conclusive at that time. Then what happened is that there was an invitation from Los Alamos to spend together a few months and to use a local computer who was faster. The local computer, so in Livermore they were using a slower UNIVAC, and the local computer was an IBM 704, which was supposed to be faster than the UNIVAC. Now, by nowadays standards, these performance are really ridiculous. So whatever smartphone that you have is millions of times more powerful than these computers. But still, Bernie Adler took the opportunity of using this computer. He came to Los Alamos, he accepted, and brought with him a molecular dynamics code for the IBM. And between June and August, he used 180 hours. So he came, not only he came, but he used like a maniac the local computer. And at the end, exchanging initial conditions between the Monte Carlo and the molecular dynamics for the molecular dynamics, and looking more carefully at the results, they both converge. And this is a conference number 3 that took place in Varena in September with a joint publication of Bill Wood and Bernie Alder. So this is basically the result where you have the pressure against the volume. So this is the dense phase, the solid line, and the fluid branch is here with the fluid and dilute fluid there. And you see that you have a first order transition in the sense of having here a discontinuity in the thermodynamic variables, the first derivative of the thermodynamic potentials. And that was really the result that allowed this, this branch, this new branch, this emerging branch of statistical mechanics, of physics, to start and to... Now, I mentioned hard spheres. Hard disk is a bit more complicated, but I think I don't have much time to go into the details. In 1 dimension, there is no phase transition. In 3 dimensions, there is a first order phase transition. What about 2 dimensions? Looks like there is a first order phase transition and a second phase transition, which is continuous. But it's very complicated, and it's only very recently that we had something that clarified the situation. Now, just a graph that shows the history after that. So I said molecular dynamics was not applicable to regular potential until Anis Rahman in 1964 published a paper where he had the good algorithm for doing that. And from that time on, molecular dynamics was used also for regular potentials, not only for hard spheres. Now that was 1964. CECAM was founded in 1969, not much later. And since then, you can see how the field has evolved in the community of science. So if you look at, this is a kind of statistics of the articles using molecular simulation. The articles on graphene, the articles on the transistor properties or renormalization group, which are 4 subjects in science. And you see how the growth of molecular simulation is taking place during the year, and is not stopping. Graphene is very impressive too, but it's an explosion at some given time. It's not very clear how much it will go later on, but well, it may continue. This depends very much on the results that are obtained. Now, on a more personal side, Bernie Alder was given the Boltzmann Medal, and that took place in 2001. Not only for these results of hard spheres, but also for something that I mentioned, which are the long time tails, and for a paper that is very important for a community of electronic structure people, which is known as a Sepperli-Alder paper. So for this, he was awarded the Boltzmann Medal, which is the highest honor that you can have in the community of statistical mechanics. And we have one other Boltzmann medalist in the audience that we are very proud to have with us. And in CECAM, we founded a prize in 1999 which we named after Bernie Adler. So there is no CECAM Prize that is awarded to a computational scientist named after Bernie Adler, and this was the award of the first Bernie Adler CECAM Prize to Professor Giovanni Cicotti. Now this is my epilogue, and what it means is the following. We have been speaking about a battle that is the Battle of Varenna. Now, when I was preparing this talk, I was also reading a history book, Patrick Boucheron, Histoire mondiale de la France. It's a very interesting book because it deconstructs a lot of things that we believe about battles and so on. This is a painting of La Bataille de Poitiers in 732. It's full of lies. Most probably there was no battle in Poitiers or in Tours, because the English people speak about the Battle of Tours rather than Poitiers. So we don't know what took place and where it happened. But most probably there were a few fights, but never a battle. And the battle is supposed to have stopped the invasion of the Muslims, of the Arabs from Spain, coming from Spain. They had conquered Spain. But in fact, a few years later, you had in Burgundy other battles. That means that this battle was not decisive at all for these invasion troops to. So you have to be very careful. But what is true that the meaning given to the Battle of Poitiers is correct. After that time, there was a confidence in the Frank tribes to organize themselves in order to reconquer their territory, which is exactly what happened in Varenna. That somehow the community organized itself and had sufficiently self-confidence and started the success of this new scientific field. Thank you very much.
Thank you, Michel.